Hello everyone, my name is Madhuri Gupta, working as an assistant professor in the Department of Computer Science, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Today we will discuss one more example of state space search, the missionaries and cannibal problems. Before that, let's have a quick recap of previous lecture. What is water jug problem? You are given two jugs with the capacity M and M respectively. Initially, they are given empty, there is an unlimited supply of water. You can either fill the whole jug or a quantity that is less than the given capacity of jugs. Now, you are also given a third positive integer d using the two given jugs. You need to come up with a solution to have d amount of water in them and return the number of steps you took to reach that capacity, and you have to follow the production rules. Rule number 1, fill a jug; rule number 2, empty a jug; and rule number 3, pour water. By using these rules, you have completed water jug problems. Now, let us begin the today's topic, the missionaries and cannibals problems. The missionaries and cannibal problem and the closely related jealous husband problem are classical river crossing problem puzzles. First, the missionaries and cannibal problem is a well known toy problem in artificial intelligence. The problem in the missionaries and cannibal problem, 3 missionaries and 3 cannibals must cross a river using a boat which can carry at most 2 people under the constraint that for both banks, if there are missionaries present on the bank, they cannot be auto numbered by the cannibals. If they were, the cannibals would eat the missionaries. The boat cannot cross the river by itself with no people on board, and in some variations, one of the cannibals has only one arm and cannot row. Let us have the solution one by one. First, let us consider that both the missionaries M and cannibal C are on the same side of the river. Left, right, initially the positions are 0 M, 0 C and 3 M, 3 C. Now, let us send 2 cannibals to left of the bank, 0 M, 2 C and 3 M. 1 C send 1 cannibals from left to right. Now, the condition is 0 M, 1 C and 3 M, 2 C. Now, send the 2 remaining cannibals to left, 0 M, 3 C and 3 M, 0 C, send 1 cannibals to the right. Now, the condition is 0 M, 2 C and 3 M. 1 C now sends 2 missionaries to the left, 2 M, 2 C and 1 M. 1 C send 1 missionaries and 1 cannibals to right. Now, the condition is 1 M and 1 C and 2 M and 2 C, send 2 missionaries to the left. Now, the condition is 3 M, 1 C and 0 M, 2 C, send 1 cannibals to right, 3 M, 0 C and 0 M. 3 C send 2 cannibals to left, 3 M, 2 C and 0 M. 1 C send 1 cannibals to right, 3 M and 1 C and 0 missionaries and 2 cannibals in the opposite side. Send 2 cannibals to left, 3 missionaries and 3 cannibals. Now, in the opposite hand we have 0 missionaries and 0 cannibals. Here shows the position of the boat after the action is performed. Therefore, all the missionaries and all the cannibals have crossed the river safely. Now, we have the another way how to solve the missionaries cannibal problem. The missionaries and cannibal problem is a classical river crossing puzzle where the objective is to move missionaries and cannibals across a river without leaving more cannibals than missionaries on either side. There are different solutions, but here is common one. Start with all the missionaries and cannibals on one side of the river, let us say the left side. Take 2 cannibals across the river to the right side, return alone to the left side. Take 2 more cannibals across the river to the right side. Bring 1 cannibals back to the left side. Take 2 cannibals across the river to the right side. Return alone to the left side. Take 2 cannibals across the river to the right side. Return with 1 cannibals to the left side. Finally, take 2 cannibals across the river to the right side. At this point, you will have successfully transported all the missionaries and cannibals to the other side without violating the constraints. Remember, at no point can the number of cannibals on either side exceed the number of missionaries. In the jealous husband problem, the missionaries and cannibals become 3 married couples, and the constraint that no woman can be in the presence of another man unless her husband is also present. Under this constraint, there cannot be both women and men present on a bank with women outnumbering men, since if there were, these women would be without their husbands. Therefore, upon changing men to missionaries and women to cannibals, any solution to the jealous husband problem will also become a solution to the missionaries and cannibal problems. So, now how to solve this problem? A system for solving the missionaries and cannibal problem, whereby the current state is represented by a simple vector M, C, B, where M stands for missionaries, C stands for cannibals and B stands for number of transition. The vector's elements represent the number of missionaries, cannibals, and whether the boat is on the wrong side respectively. Since the boat and all of the missionaries and cannibals start on the wrong side, the vector is initialized to 3, 3, 1. Actions are represented using vector subtraction or addition to manipulate the state vector. For instance, if alone cannibals cross the river, the vector 0, 1, 1 would be subtracted from the state to yield 3, 2, 0. The state would reflect that there are still 3 missionaries and 2 cannibals on the wrong side, and that the boat is now on the opposite bank. To fully solve the problem, a simple tree is formed with the initial state as the root, the 5 possible actions 101, 201, 011, 021 and 111 are then subtracted from the initial state, with the result forming children nodes to the root. Any node that has more cannibals than missionaries on either bank is in an invalid state, and it is therefore removed from further consideration. The valid children nodes generated would be 320, 310 and 220. For each of these remaining nodes, children nodes are generated by adding each of the possible action vectors. The algorithm continues alternating subtraction and addition for each level of the tree until a node is generated with the vector 0, 0, 0 as its value. This is the goal state, and the path from the root of the tree to this node represent a sequence of actions that solve the problem. So, here is the solution. The earliest solution known to the jealous husband problem using 11 one-way trips is as follows. The married couples are represented as alpha, that is male, and a female beta and B and gamma and C. Timeline solutions to both jealous husband and missionaries and cannibals problem with the vertical axis denoting time, blue denoting husband or missionaries, red denoting wives or cannibals, yellow denoting the boat, and lines of the same type denoting married couples in the jealous husband problem. The solid red line optionally denotes the cannibals unable to row. In the right figure, if a wife or cannibals staying on the boat count as being by herself, a shorter solution is possible as shown in the table 1. This is a shortest solution to the problem, but is not the only shortest solution. If however, only one man can get out of the boat at a time and husband must be on the shore to count as with his wife as opposed to just being in the boat at the shore. Move 5 to 6 is possible, for as soon as lambda has stepped out, B on the shore won't be with her husband despite him being just in the boat. As mentioned previously, this solution to the jealous husband problem will become a solution to the missionaries and cannibal problems upon replacing men by missionaries and women by cannibals. In this case, we may neglect the individual identities of the missionaries and cannibals. The solution just given is still shortest and is one of 4 shortest solutions. If a woman in the boat at the shore but not on the shore counts as being by herself, that is not the presence of any man on the shore, then this puzzle can be solved in 9 one-way trips as shown in the table 2. Let us understand one of the variations. An obvious generalization is to vary the number of jealous couples or missionaries and cannibals, the capacity of the boat or both. If the boat holds 2 people, then 2 couples required, 5 trips, and 4 or more couples. The problem has no solutions. If the boat can hold 3 people, then up to 5 people can cross. If the boat can hold 4 people and number of couples can cross. A simple graph theory approach to analyzing and solving these generalizations was given by Farley, Cook and Drake in the 1966. If an island is added in the middle of the river, then any number of couples can cross using a 2-person boat. If crossing from bank to bank are not allowed, then 8 n minus 6 one-way trips are required to ferry n couples across the river. If they are allowed, then 4 n plus n trips are required if n exceeds 4, although a minimal solution required only 16 trips if n equals 4. If the jealous couples are replaced by missionaries and cannibals, the number of trips required does not change if crossing from bank to bank are not allowed. If they are, however, the number of trips decreases to 4 n minus 1, assuming that n is at least 3. Now, let us have some history related to missionaries and cannibals problem. The first known appearance of the jealous husband problem is in the medieval text Propositions ad Acundus Janus, usually attributed to Acklin. In Acklin's formulations, the couples are brother and sisters, but the constant is still the same. No woman can be in the company of another man unless her brother is present. From the 13th to the 15th century, the problem became known throughout northern Europe, with the couples now being husband and wives. The problem was later put in the form of masters and valets. The formulation with missionaries and cannibals did not appear until the end of 19th century. Varying the number of couples and the size of boat was considered at the beginning of the 16th century. Cadet de Fonety considered placing an island in the middle of the river in 1879. This variant of the problem with a two-person boat was completely solved by Ian Pressman and David Sigmaster in 1989. In 2020, controversy surrounding the racist theme in a cartoon about the problem led an AQA exam board to withdraw a textbook containing the problem. Now we can have another example, that is wolf, goat and cabbage problem. The above illustrated illustration depict the wolf, goat and cabbage problem in the Orbesis Prester dating to 1215 to 1330. The wolf, goat and cabbage problem is a river crossing puzzle. It dates back to at least the 19th century and has entered the folklore of several cultures. The story: a farmer with a wolf, a goat and a cabbage must cross a river by boat. The boat can carry only the farmer and a single item. If left unattended together, the wolf would eat the goat or the goat would eat the cabbage. How can they cross the river without anything being eaten? So, here is the solution. In the above diagram, the two solutions with the vertical axis denoting time and brown, grey, green and being paths denoting the wolf, goat, cabbage and boat respectively. The first step that must be taken is to let the goat go across the river, as any other actions will result in the goat or the cabbage being eaten. When the farmer returns to the original site, he has the choice of taking either the wolf or the cabbage across next. If he takes the wolf across, he would have to return to get the cabbage, resulting in the wolf eating the goat. If he takes the cabbage across second, he will need to return to get the wolf, resulting in the cabbage being eaten by the goat. The dilemma is solved by taking the wolf or the cabbage over the bringing the goat back. Now, he can take the cabbage or the wolf over the finally return to fetch the goat. Here is the action in the solution are summarizing in the following steps. First, take the goat over. Second, return empty handed. Third, take the wolf or cabbage over. Fourth, return the goat. Fifth, take whichever wasn't taken in step 3 over. Step 6, return empty handed. Step 7, take the goat over. There are 7 crossing, 4 forward and 3 backward. Note, the key to the solution is to realizing that one can bring things back. This is often unclear from the wording of the story, but never forbidden. Knowing this will make the problem easy to solve even by small children. The focus of the puzzle is not just task scheduling, but creating thinking similarity to the 9 dots puzzle as shown in the figure. Let us have the visualization of this puzzle. Uppercase letters denotes the fox, goes and beans at the destination, and lowercase ones denotes them at the origin. Movement of each object is represented by a coordinate axis. All the 8 valid and invalid placements are shown as vertices of a cube and all 12 movements as its edges. Invalid moves are crossed out, leaving the 2 solutions shown in blue and purple. Feel free to ask if you have any questions or need further clarification. Now we have to know about the summary of our missionaries and cannibals problem using state space search. The missionaries and cannibals problem involves transporting a group of missionaries and cannibals across a river in a boat while adhering to certain constraints. The challenge is to find a sequence of valid moves that allows all individuals to safely reach to the other side without violating the rule that at any given point the number of cannibals cannot exceed the number of missionaries on either side. The problem can be modeled using state space search, where each state represents the configuration of individual on both sides of the rivers and boat's positions. The objective is to navigate through the state space, exploring possible moves while ensuring that no state violates the cannibals missionaries constant. The goal is to reach a valid end state in which all individuals have successfully crossed the river. Now we have the applications of missionaries and cannibals problems in today's world of artificial intelligence. While the missionaries and cannibals problem itself may not have a direct application in today's world of AI, its underlying concept of state space search, constant satisfaction and optimization can be unlocked to certain real world scenario involving artificial intelligence and decision making. Here is how. Research allocation and scheduling. In AI driven resource allocation and scheduling problem such as allocating tasks to robot in a warehouse or scheduling appointments for healthcare professionals, the constraints and objectives can be similar to those in the missionaries and cannibals problems. Ensuring that resources analog to missionaries and cannibals are allocated optimally while adhering to constraints can be approached using state space search techniques. Second, transportation and logistics. The problem of moving goods or vehicles between locations while considering constraints such as weight, capacities, time, window and traffic conditions bears resemblance to the missionaries and cannibal problems. Artificial intelligence algorithm can be employed to find optimal routes and schedules similar to how the puzzle aims to find a sequence of valid moves. Third, multi-agent systems. In scenario involving multiple agents with diverse goals and constraints like coordinating drones for search and rescue missions or managing autonomous vehicles in a city, state space search concept can be applied to ensure efficient collaboration while avoiding conflict or violating rules. Game AI and puzzle solving. While not a direct real world application, the missionaries and cannibals problem showcases problem solving techniques that can be useful for developing intelligent agent capable of solving complex puzzles or making strategic decisions in various games and simulations. Overall, while the missionaries and cannibals problem itself may not be directly application to modern AI applications, its fundamental concept provide a basic for designing algorithms and strategies to tackle more complex real world problems involving optimization, constraint satisfaction and decision making. In summary, we need to move all of them missionaries and cannibals to right side of the river. For that we have to follow the rules. First, the boat can carry at most 2 people. Second, if cannibals numbers greater than missionaries, then the cannibals would eat the missionaries. Third, the boat cannot cross the river by itself with no people on board. So, we have solved 3 problems of state space search, that is water jug problems, we have solved missionaries cannibal problem and we also solved 8 puzzle problems. So, we have learned what is state, that means the position and where the problem starts. that is state, and where the problem ends, that means initial state and the goal state. And we have also learned about the transition, that means how the state transfer from one state to another state to reach toward our goal. And we have explored so many things about 8 puzzle problem, like how the tiles can be moved, how we can use the operations like up arrow, down arrow, right arrow, left arrow, so that we can solve our state space problem. And in water jug problem, we have different amount of water and we have different goal conditions. We solve in 11 steps, that is production rules, where we have to follow all the values so that we can reach toward our goal. We have different goals in different initial states. And now in the missionaries cannibal problem, we have solved the missionaries cannibal problem by following the rules, and we also contradict it with the husband and wife problems. We go through with all the states and we have gone through with all the steps necessary to follow. We also gone through with the side by side allocation of state, how the right side conditions follow, how the left side condition follow, and finally we got our goal. So in the summary, we can say that the state space problem is a classical AI problem where we have to solve our problem in the limited state, in the limited area, that is state space, and we have to follow the matrix condition, that means we have to follow how the matrix can be divided, how the limited condition can be follow. And also we have to concentrate about the time complexity and space complexity, about how much time it will take to solve and how much space it is needed to solve the problem. And we also gone through with the operators, that means how the steps or agent can be take the action to perform the particular action. And we also gone through with a lot of criteria, or you can say constants, to follow the problem or to solve the problem. So in summary, we can say that the state space problem can be solved using some production rules, some operators, some states and some operators to solve the problems. So we have some limitation of state space search, that there is no specific schedule how to pick up the rules and how to solve the problem. Here we do not know about the exact step to follow, means which steps we need to take first and we need to take the second steps. We randomly pick the steps, we do not have any systematic approach. So in the next chapter we will go with the search, where we have the systematic approach of how the step by step we can follow the rules. So in the next chapter we will go with the depth first search and breadth first search, which will define you a systematic algorithms where you can solve the problem in a step by step manner and in a exact way. So in summary, we can say that 8 puzzle problem, water jug problem and this missionaries cannibal problem use the production rule, where we randomly pick the steps and we have some constant to follow and we get the solution. So thank you so much and we will see you in the next chapter.